Hello friends, welcome back to this lectures on quantum mechanics in the relativistic regime. So last week we have been looking at deriving the first relativistic wave equation. So we started by looking at writing down the dispersion relation or the relation between energy and momentum in the relativistic space. So just to repeat that we are using natural units all through this course. So where h cross and c is equal to 1. So in the initial part of the course, when we revised the quantum mechanics, we have set explicitly we have not set this h cross and c is equal to 1, but now in the relativistic case when we are studying, we will set h cross and c is equal to 1. Given that, we realize that in the relativistic energy momentum relation is always quadratic. So E square is equal to P square plus M square. Now if you want to proceed in the former in the same way as we have proceeded for the Schrodinger equation, so we have to take the square root of this E square is equal to P square plus M square, and that leads to it is inherently nonlinear relation essentially, because there is a square root. If you expand the square root, you will end up having operators which are much higher, and if you identify momentum with a derivative operator, so this would mean that you will have series of higher and higher derivative operators. So if you take the square root, now this is not what we wanted, and so what we do was that because this leads to a lot of issues, because higher derivative theories are not attractive but also not desirable because host of problems which we discussed last time. So instead of that, we just keep the E square is equal to P square plus M square as it is. We do not modify it, do not take the square root, and then substitute E is equal to I del by del t, I h cross del by del t, and then setting h cross is equal to 1. So there is a h del by del missing here. Okay, let me put it this back. And P is equal to minus I h cross del, okay, and then setting h cross is equal to 1, we end up having the first relativistic quantum mechanical wave equation, which is quadratic in time, quadratic in space derivatives and time derivatives, and it has equal number of time derivatives and space derivatives, unlike the Schrodinger equation, and this is the so called Klein-Gordon equation, where you can re-express it as with a box plus m square phi is equal to 0, where box is equal to del square t minus del square h. So this is our first relativistic wave equation, and now let us see the properties of this one essentially. Now let us try to solve this. Now this wave equation, let us say that it has solutions which are plane wave. It is free in the sense that there are no interactions as of now, no potential, so we will look for free particle solutions for this wave equation. Now obviously this wave equation is should have because in analogy with quantum mechanics and with any other wave equation, we would expect to have these equations to have solutions which are plane wave. To this equation. So you would expect phi, which we introduced now, okay, to have solutions phi of x mu, or that is equivalent phi of x bar t to have solutions which are proportional to e power minus I k dot x, where k dot x is equal to k mu x mu, that is equal to k 0 x 0 minus k bar x bar. So, k 0 where P is typically identified with P is equal to h cross k. So, this is nothing but k 0 is nothing but energy, essentially x 0 is equal to time. So, this is nothing but e power minus I e t minus k x essentially. So, e power minus I e t minus k bar x bar. Okay. I don't let me just re-write it the parenthesis one more time just for legibility. So, just make sure now putting back, okay, legibility. Now, let me put this back into the wave equation, putting this plane wave test solution. This is now a test solution. So, I say that this equation should have plane wave equations, where here where I wrote this n is nothing but normalization factor. Okay, this is nothing but a normalization factor. So, putting this plane wave test solution back into the Klein-Gordon equation, we have, so I put back and you get the energy of the wave to be E square is equal to k square plus m square. So, it satisfies the relativistic energy momentum relation essentially, and E is essentially plus k square plus m square. So, it satisfies the energy momentum relation with the definition that E is equal to plus k square plus m square. Now, this energy momentum relation, the relativistic energy momentum relation would also is if you take the square root, both the solutions are possible, both positive and negative. Okay. So, instead now one can argue that suppose if I take instead of phi a solution which is e power I k mu x mu, here we took minus k dot x essentially. Okay. Instead of taking the minus sign, you can take the plus sign essentially, plus sign. So, that would corresponds to E is equal to minus k square plus m square. We will come to the physical interpretation in a second. Let me just put it back into the Klein-Gordon equation, and this, when I put it back into the Klein-Gordon equation, this also gives me E square is equal to k square plus m square. So, it satisfies the relativistic energy momentum relation, but then you notice that I have taken energy to be E is equal to minus of k square plus m square essentially. So, this also satisfies. So, let me put it with the plus sign here, the normalization just to change as the okay, minus sign essentially. Okay. So, minus sign for the normalization, plus sign for the this thing. So, this also satisfies the Klein-Gordon equation. So, what we have here is that a situation in which there are two possible solutions for the energy corresponding to plus and minus signs of corresponding by taking the plus and minus signs of the square root of the k square plus m square, and for both plus and minus the Klein-Gordon equation does not make any distinction and it satisfies the solution. It provides an equal solution to both positive and negative energy solutions. So, the Klein-Gordon equation Kg equation satisfies both positive energy and negative energy solutions in the same manner. Okay. So, the Klein-Gordon equation satisfies the positive and negative energy solutions in the same manner. So, now let us come to the physical interpretation. As far as the thing is concerned, so you are saying that you can have waves with negative energy and the Klein-Gordon equation just satisfies them in the relativistic case essentially. So, in the same manner it wants to satisfy. So, now are the negative energy solutions physical. Now, in physics we never hear about negative energy essentially. So, we think that negative energy solutions are completely unphysical. Okay. So, they should not be present. Then what does it mean to have negative energy solutions? What does the Klein-Gordon equation mean by admitting negative energy solutions? Now, you can go completely philosophical and ask this questions that whether maybe these negative energy solutions can be completely thrown out, number one, or the number two is that the equation itself could be wrong, but the equation satisfies is derived just by imposing quantization conditions on the relativistic dispersion relation. Now, how can it be go wrong essentially, that is the question. So, you have two outcomes. One, remove, neglect unphysical negative energy solutions, or 2, Klein-Gordon Kg equation is wrong. Now, both these are incorrect actually, both these approaches are incorrect, and we will see the in various cases essentially why the first situation, that removing unphysical negative energy solutions or neglecting them, saying that okay, I do not care about this negative energy solution, I throw them away, okay, and does it make any sense, or I mean then you will end up having problems, will lead to problems which we will see later on essentially. To problems when interactions are put in. Now, as long as you are in the free theory, that means there are no interactions, you are not putting any potential, or you are not considering any system in which there is a completely free Klein-Gordon field or Klein-Gordon particles, wave functions. Okay. So, you can neglect you can say that I remove the negative energy solutions, I do not really care and everything. but the moment you put in little bit of electromagnetic interaction or a step potential or any other kind of interaction, you see that removing this unphysical negative energy, what we call as unphysical negative energy solutions, will lead to a lot of problems essentially. So you cannot make any proper predictions, you will end up having lot of unphysical situations essentially, which will lead to several complications. So the first step itself is fraught with problems. Okay. So this method of say neglecting, so there is some deeper understanding we need in relativistic case, so I neglect it, so for the present I do not care and everything. This kind of approach will not really work. The second choice we have is the KJ equation itself is wrong. Now why the KJ equation should be wrong? We have used, okay, there is no physical reason to say, or there is no reason, because this is the first situation where relativistic energy momentum relation and quantization conditions are used. Now why should it be wrong? And if it is wrong, we should be understanding why it is wrong essentially. We do not have a deeper picture, we do not have something. Now there is a third approach which we will try to solve. What we will say is that okay, both this, is there a possibility that the negative energy solutions are not unphysical but they are physical. Okay. Okay, the negative energy solutions are not unphysical but they are physical, they could be somehow interpreted as some other things. So these wave functions do not have some negative unphysical meaning, but they have some physical picture. Okay. So that is the third approach, negative energy wave functions have some physical meaning. So perhaps have some physical meaning is the method which actually finally works essentially. This is what I can tell you the answer that it is, but we can actually start looking into it. Okay. And we will see how it works essentially in a second. Okay. So the third approach would be that maybe negative energy solutions have some physical meaning. Though they may have some physical meaning. So you start with this. So what we should see, okay, this is the basic idea we will try to approach. So the first two, like I said, that suppose if I remove or neglect negative energy solutions, that works very fine as far as we have only free particle situations. As we will see later on, it will lead to problems the moment I put in interactions. So if I put in interactions or if I put a potential or something, it will lead to problems. And the second approach, that KJ equation itself is wrong, meaning it has no physical basis, why it should be wrong. Okay. So these two, because anyway we should explore why it should be wrong if it is wrong also. Okay. These two approaches are so instead of these two approaches we follow a third approach, okay, which is some sort of a middle ground. So the middle ground tells you that okay, the KJ equation is correct and the negative energy solutions are not completely unphysical, they are not unphysical, but they may have some physical interpretation, they have some physical interpretation. In view of this, we can write down the most general solution for the KJ equation as phi of x t some normalization constant, some constant e power minus I k x, again k x means k mu x mu essentially, plus b e power plus, okay, I k x. So, now this is the basic picture, this is the most general form you can have for the Kg equation. Okay. Now, let us look at what would be, now let us try to proceed, okay, let us try to proceed how we want to interpret. Now you see that there is a solution for phi, there is a solution for phi star, which is the complex of phi, complex conjugate of the. Now if you take the phi star, you can see that it is the opposite essentially, so phi and phi star. So we can say that phi has positive energy solutions and phi star has negative energy solutions. So you can have imagine that, okay, phi and phi star have opposite energy solutions. Before doing further, okay, let us do something simpler, just try to get a clue, okay, to get a clue how to make these phi and phi star positive and negative energy solutions, if there is any clue, okay, if there is any clue, okay, if there is any clue to get physical interpretation of these negative energy solutions. Now for that, let us derive the continuity equation for the Klein-Gordon field. So the basic idea here is that if I derive the Klein-Gordon field, so you remember for in ordinary quantum mechanics, in non-relativistic quantum mechanics, there is a continuity equation there is a continuity similar to what is in electrodynamics. So which we, I think if I remember correctly, we mentioned it in the part somewhere in one of the early reviews. Did we see it? I will just check it 1 second. Okay, I think I mentioned it, but anyway we can do it anyway. The relativistic the non-relativistic Schrodinger equation is given by h cross square by 2m del psi by del t is equal to h cross del square psi is equal to minus I del by del t psi essentially. Okay. Now you can write the equation for psi star, okay, and that will give me h cross square by 2m, okay, del square psi star is equal to psi h cross del by del t psi star. So you can multiply the thing with psi star and this with psi multiplication, and that gives me something called the continuity equation. So, the continuity equation tells you that take the difference of it essentially. So, the continuity equation tells you that del rho T plus del dot J is equal to 0. You can re-express it exactly in this fashion in quantum mechanics. I will just put a psi. Okay. This tells you that now rho psi, just to tell you that this is quantum mechanics. This has the same expression as in electrodynamics, classical electrodynamics. Now rho psi is equal to psi star psi integrated over all the space essentially, and J psi is equal to psi star del psi minus psi del psi star. So, this gives you sort of the flux, this gives you the probability density. Now, this continuity equation in non-relativistic quantum mechanics is a very important equation which tells you that the probability is conserved at every instant of time, essentially at every instant of time. In quantum mechanics, the probability of finding a particle is always conserved essentially in any system, in a quantum mechanical system. Now, let us try to do the same thing for a relativistic case. So, just to get a clue what we are meaning, because we are finding problems with negative energy solutions, will there be any way of introducing this negative energy, giving a physical interpretation for these negative energy solutions? That is the basic idea. Now, for that I do the same procedure. So, I take the Klein-Gordon equation instead of the Schrodinger equation and take the complex conjugate of it, multiply the original equation with phi star, okay, and then the conjugate equation with psi with phi, and take the difference between these two, and this you can re-express the continuity equation in the relativistic formulation as follows. In relativistic formulation, if you write in terms of 4 vectors, it becomes very simple. So, this is your continuity equation, simple, where J mu is defined as phi star del mu phi minus phi del mu phi star. Okay. So, this is the continuity equation in the relativistic sense. Now, let us look at the components of J mu. J mu is the probability current, the 4 component. Now, J mu has J bar, which is the flux essentially rho and J bar. Now, rho J0 is phi star del by del T phi minus phi del by del T phi star. Okay. J0 is nothing but rho is equivalent to this. Okay. Now, compare this with the rho in the previous expression, okay, in the relativistic sense. In the non-relativistic case, Rho is just a number, it is a radius essentially. So psi star psi, it is nothing but a modulus, essentially modulus of a complex number essentially. It is always positive definite. Okay. Modulus of a complex quantity. Okay. If you want to contact complex number, always positive definite. So this is a very important thing. In the non-relativistic case, we keep saying that rho is always positive, so that means it is always positive. It is always conserved, and we give an interpretation for it essentially that the probability density is always positive. It means that you can have a physical interpretation that you will find a particle at some point essentially, in some point in space and time essentially, in the given plane. Now in contrast, now let us see what is J0. J0 is phi del by del t phi del by del t phi star. This is a consequence of having two time derivatives in the equation of motion. Now if we have two time derivatives in the equations of motion, and when you do the analysis which we did earlier, essentially you will end up having the definition of the probability density to be a time dependent quantity. Now there is no way we can insist that this is positive definite, because you see the minus sign in between, and you can always, because it is a meaning you can always choose the initial conditions such that the rho could be negative, and it is allowed. Okay, it is allowed. The initial conditions could be such that rho could be negative. Now you can see it from this equation itself essentially. Now you can always choose an initial condition, because you have to give two initial conditions while solving the Klein-Gordon equation, because it is a quadratic differential equation. So you have to choose phi and del phi by del t, you have to give two different initial conditions. So suppose if I choose a very different initial condition, okay, for del phi by del t, such compared to the initial condition for phi or so on so, okay. Now this can lead to negative values. You can easily see that it can lead to negative values for rho, okay. Now how will you interpret a probability density or a probability with negative values, okay, but it gives you a clue, okay. I'll tell you why it gives you a clue. So by definition probability density should always be positive, it should be a positive column, and that is satisfied in non-relativistic quantum mechanics. But in relativistic quantum mechanics, the moment you write down the first equation, the first pathology we find is that, okay, there are negative energy solutions. Secondly, now if we are trying to give an interpretation for that, and we ended up having the rho to be in positive instead of being positive definite, okay. So it is negative. So the probability density interpretation interpretation is in trouble, because by definition probability density cannot be negative, which very hard. By definition cannot be negative. So for okay, so that is one thing. Okay, that is one problem we have essentially. Okay, now so the current is fine. Essentially, the current will be just I'll just write down the current also. Essentially, the current J bar is equal to phi star del phi minus phi del phi star. Okay. Okay, so together these equations have a problem. Now this is a problem. Now is there a way out of this? Is there a way out of this? Is there a way? Like I told you that I will give you a clue. Okay, I will give you a clue that this that the moment you write the continuity equation, we will try to get a clue what could this be, what to do with the negative energy solutions, essentially negative energy solutions. Okay. Okay, so the point is that is there a way? Now you see that when can be a rho negative? If instead of let's not call it as a, let's not call it as a probability density. Okay. Now suppose if we imagine that remember, go back to electrodynamics. Now go back to electrodynamics and imagine that you have a system of particles made up of both electrically positive and electrically negative charged particles. Okay. So both positively charged particles and negatively charged particles. Now you take this system. Now in this system the electric density, charge density, electric charge density can be negative if the number of negatively charged particles are more. Similarly, it can be positive when the number of positively energy charged particles are more, essentially. Okay. So in this case what happens is, both if a system of both negatively charged particles and positively charged particles are coexisting in a system, essentially, then the rho or the charge density, instead of probability density, if we call it as a charge density, then it can be negative. So what we are seeing, okay, the entire point is that what we are seeing, okay, this rho should correspond to this rho should correspond to positively charged particle or meaning charged electric charge density containing both positively charged particles and negatively charged particles. So in that case what happens? You can have rho negative. So you do not interpret rho as probability density, but rho is defined as electric charge density and J would be defined as electric current density. Now very good, this is a good way out, but where are these two particles? Where are these two particles essentially? Yes, there are there any two particles in the system? We are only talking about one wave equation, but they exist, they are both there essentially. Here you have phi with positive energy solution. Okay. So phi is a positive energy solution, so I can call it as a positively charged particle essentially, or some negatively charged particle. We can give the interpretation once we couple it with the electromagnetic field essentially. One second. Then phi star negative energy particle solution. Okay, this is what we saw, right? As in phi is e power I kx, and phi star would become e power minus I kx, or e power minus phi is equal to e power I kx. So negative energy particle would be e power I kx essentially. So plane wave. Now if phi contains an electric charge which is some q, electric charge of phi is q, then phi star would contain, and if the would contain minus q electric charge. If phi star would contain minus q electric charge, then both of them together are existing. It is a two particle solution first of all. Okay. Now we are no longer dealing with one particle solution, it is a two particle solution. Okay. And this two particle solution can solve, we can interpret it as a two particle solution. The Klein-Gordon equation necessarily becomes a two particle solution. Okay. The Klein-Gordon equation necessarily becomes a two particle solution with one positive energy, another negative energy, and each of them having opposite quantum numbers essentially, or electric charges. So this is the interpretation which can be made viable essentially. This can be made viable. So we can interpret the Klein-Gordon equation, or the solutions of Klein-Gordon equation admits two particle solutions and what are the property these two particles have? Such that the two particles have same mass, 2, one is positive energy solution, another is negative energy solution, and third, both have opposite electric charges. Okay. So this is the interpretation which will work for the case of the Klein-Gordon equation. So this is the interpretation which will work for the Klein-Gordon equation. So now they should have equal masses, because we have seen the Klein-Gordon equation, the mass is not changing. So k square is equal to m square, m is always the constant essentially, m is the same for a negative energy solution or positive energy solution, as you can see here essentially. E is equal to plus, because only the square root is changing. Okay, the sign of the square root is changing. So the mass remains the same. Okay, so the mass remains the same. So they have the same masses. they have opposite charges, because we see that that is the only way we can make this rho negative. That is the only possibility you can make it rho negative. Now I will make it more concrete in the next lecture, essentially by actually coupling it with the electromagnetic field. Okay. And the third one is that one of them is a positive energy solution, another of them is a negative energy solution. Now the particles which have the same mass, opposite charges, and with one of them positive energy and negative energy, this pair of particles are called particle antiparticle solutions, essentially particle and antiparticle. The particles which have the same mass, opposite quantum numbers or opposite charges are called antiparticles of this solution. Okay. So for the first time, relativity automatically admits antiparticle solutions, essentially, and we will see the consequences of it in a coming day. So this is a relativistic wave equation admits particle antiparticle solutions where antiparticle is defined as same mass and spin this we will see later, spin of the particle, but opposite electric charge and negative energy solution. Okay. So what we have seen is that the Klein-Gordon equation admits particle antiparticle solutions, and so we will recap this in the next lecture. And so for the first time we have seen the solutions of Klein-Gordon equation, and what we will do is in the next class we will actually couple it with the electromagnetic field and make these interpretations much more completely concrete, because we are so far we have not put any electric charge for these fields. Essentially we have not coupled it with electric field and then shown that it has a positive charge or this has a negative charge. So this is what we have to show explicitly, and then we will be able to interpret this thing in a more concrete fashion. So I will stop here, okay, and then I will meet you in the next lecture. Okay. Thank you.